Imagine you're a robot and you don't know exactly where you are. Your wheels spin, you can move, but error accumulates with every step. This is called odometric drift, and it's the core problem of model road localization. The extended common filter is the algorithm that solves it. In this context, the robot navigates autonomously in an environment with visual markers called April tags, placed at known positions in the map. The filter fuses two sources of information: wheel encoders, which are frequent but drift over time, and the April tag detections, which are noisy but absolute. Every time the robot sees a known tag, it has a global reference that anchors the estimate. Without that anchor, odometric drift will make any navigation system unreliable within seconds. The extended column filter is a Bayesian probabilistic estimator. It doesn't say the robot is here, it says the robot is here with this uncertainty, and represents that explicitly as a Gaussian distribution. An estimated pose and a covariance matrix describing how spread out that estimated is. The reason it's extended is that differential-driven motion is non-linear. The extended Kalman filter handles that by linearizing locally with Jacobians at every cycle. So how does it work? The pipeline alternates between two steps on every control cycle. In the predict step, the robot integrates wheel velocities to propagate the estimated pose forward in time. Simultaneously, it propagates the covariance throughout the Jacobian of motion model. Uncertainty grows because error integration introduces error, and that growth is explicit and quantified. In the update step, if the camera detects an April tag, the filter computes the difference between the actual measurement and what it's expected to see from its current estimated pose. Before applying that correction, it goes through a Hanapolis gate. If the discrepancy is statistically inconsistent with the current covariance, the detection is discarded as an outlier. If it passes the gate, the Kalman gate weighs how much to correct, and both the pose and the covariance are updated. Uncertainty drops. There's an additional resilience mechanism. If the filter reacts to many consecutive detections, it assumes the accumulated drift is too large to recover from immediately, and executes a hard reset. It recomputes the pose directly from the geometry of the most recent April tag and inflates the covariance so that subsequent detection can redefine it quickly.
Before the robot can navigate autonomously, it must first understand and represent its surroundings. Since the environment is initially unknown, the robot must continuously estimate its position while building a map of obstacles and free space. Our pipeline begins with Monte Carlo localization. Using odometry, we apply that reckoning to predict the robot's motion, while a particle filter and analytical field sensor model use LiDAR measurements to determine the most probable robot pose. With this pose estimate, we perform SLAM to build an occupancy grid map. LiDAR measurements are projected into the global frame, and Bresenham's algorithm is used to identify free and occupied cells. The map is updated using a probabilistic log-odds representation, allowing occupancy information to accumulate over time. Finally, we apply loop closure through graph SLAM to correct accumulated drift. When the robot revisits a known area, additional constraints are added to the pose graph, which is then optimized using the Levenberg-Marquardt algorithm. This results in a globally consistent trajectory and a more accurate map.